This begins our Unit 8 notes on exponential and logarithmic functions. So we are in day 1 of this unit, and here are our learning targets. So at the end of this lesson, you want to be able to say that I can identify an exponential growth function and an exponential decay function, as well as graph both of those, so that I can solve word problems that involve exponential growth and decay, and I'll know I've got it when I can do the practice problems in my notes and my math space homework. Alright, let's dive into today. So we should have our note packets open to Unit 8, Day 1, Exponential Growth and Decay. We're going to begin with graphing these 6 functions. So these are all going to be exponential functions, and you can see that because they're a number to the x power. Okay, so these are all exponential functions. Go ahead and put them into your graphing calculator, and then you'll be able to see the shape of them, and then use your table features so that you can actually plot certain points. So pause the video here so that you can put those into your calculator and sketch them. Alright, what I did was I just took a screenshot of the answer key and pasted that here. It has all the graphs, and then they're all color coordinated here. So let's go ahead and use these graphs to answer some of the following questions. So for each, we're going to look at just number 1 and number 2, so it's a little flipped, but this is number 2. So number 2 here is our red. We're going to look at the red line. We want to identify, first of all, what is the end behavior. So as x is going to infinity, what is happening to f of x? What is happening to my y? Well, hopefully you can see that it's going towards 0. And as I go to negative infinity along this line, as I keep getting smaller and smaller, my y value is actually getting greater and greater and greater. So that's going to infinity. But we do have an asymptote. So what is the asymptote that we have? Is there a vertical asymptote? No, right? Because we can have any x value. But we do have this horizontal asymptote at y is equal to 0. So then using those, you can identify the domain and the range. The domain, it's all real numbers, and the range, well, we can't be below 0, so we start at 0 and we go to infinity. And then lastly, hopefully you were able to identify the y-intercept, but what happens when you plug in 0 into x, you get the point 0, 1. Now let's look at the line y equals 2 to the x. So I believe this was, yes, it was the blue line. So we're looking at the blue line. What happens? As x goes to infinity, our f of x is going to infinity as well. And as we go to negative infinity, our y is going to 0. What is our asymptote here? Hopefully you realized it was the same thing, y equals 0. Domain, all real numbers. Range, well, we can't be 0, but we can go from 0, a little above 0, to infinity. And then what's the y-intercept? Ooh, looks like they intersect, so 0, 1. And same thing would happen. I would plug in 0 for x, and I would get y is equal to 2 to the 0th power, which anything to the 0th power, you should know, is 1. Great. So, what were the similarities that you see in these graphs? Well, they have the same domain, they have the same range, their y-intercept was the same, right? Because they were all to the 0th power. Their x-intercept, this is actually an error. There was none. There wasn't an x-intercept, right? And what about their asymptote? Well, we see that they both had a horizontal asymptote of y is equal to 0. So these functions are what we call exponential growth functions and exponential decay functions. Let's define those. So exponential growth functions, as the value of x increases, the value of y also increases. Okay, key, this is huge. X increases and y increases. A quantity that exhibits exponential growth increases by a constant percentage each time period. So for example, think about interest in a bank. That's the classic example that's used for exponential growth. Your money, if you have a savings account, your money increases each year by this constant percentage. So over each year, it's this constant interest percentage that you are receiving. Okay, so that's our exponential growth. Increase, increase. Whereas exponential decay, x increases and y decreases. Okay, so a quantity that exhibits exponential decay decreases by that constant percentage each time period. So maybe you're losing money each year just by some constant percentage. That's not what you want, but that is exponential decay. Or you can think about something decaying, right? That means it's going down, it's decreasing as the time increases. So we want to think about the above graphs that we did and think which ones represent exponential growth and which ones represent exponential decay. Well, if we look back up here, the ones that are growth are the ones that are as x is increasing, y is increasing. So that's our purple, our blue, and our green, right? Which is 1, 3, 5, and 6. Whereas the decay is represented by as x increases, y decreases. So that would be 2 and 4, the red. Okay, so you can tell the exponential growth and decay by looking at your graphs. Alright, let's move on. So here's our general formula for exponential functions. So this is our new function that we're learning how to graph this unit. X, right here, the AB to the x, call the x the exponent. A is the initial value when t is equal to 0. So it's the starting point of each graph. Okay. Whereas b we called the base. Okay. So a initial value, b the base. Think with a, think like the initial amount of money that you put into the bank. The initial amount of money that you have that maybe you're going to lose over time. Whereas B is the base, okay? That's what we call it. So here is a way that we can tell if we have growth or decay. If B is greater than 1, then f of x is an exponential growth function. The percentage increase is the rate of increase or growth rate. The growth factor we find by B is equal to 1 plus R, okay? And then, that's in contrast with exponential decay. If 0 is less than b, is less than 1, then f of x is an exponential decay. The percentage decrease is the rate of decrease or rate of decay. That's what we call it. The decay factor is given by b is equal to 1 minus r. Alright, let's actually see that play into effect. How do we actually use this? So with these functions here, we want to graph them on our graphing calculator. So pause the video here to graph them so that you can see what they actually look like and get a better idea of what is meant for exponential growth and decay. If you want to use a Desmos calculator, feel free to do that as well. To graph those all and see them, now let's actually apply this general formula and these rules to determine if we have growth or decay. So for our first one, f of x is equal to negative 2 to the x. Do you think that's growth or decay based off of these two definitions here? It is growth. Why? What makes it growth? Well, our 2, that's our b value, is greater than 1. Okay. And now let's look at our second one. So what is our b value here? It's 0.3. Is that less than 1? You bet it is, so therefore it is decay. 0.3 is less than 1. About 3 to the negative x. Now this one's tricky. Is this going to be decay, growth or decay? It's going to be decay. Why would it be decay, do you think? It's because of that negative x. So that negative x makes it a decay. For that is that when we have a negative exponent, right, we can always bring that to our numerator, so we could actually rewrite this as 1 over 3 to the x, which is equal to 1/3 to the x, which then we see that b is actually less than 1. Okay, hopefully that helps. So 0.3 to the x, this should be pretty obvious now. It's decay. 0.3 is less than 1. And here we have 0.3 to the negative x. Ooh, think about this one carefully. It is growth because of that negative x again. So here I have 1/3 to the negative x, right? 1/3 to the negative x, and when I have that, I would actually flip it, and it would become 3 to the x. Interesting, right? Okay, moving on. That's defining whether we have growth or decay. Alright, down here you have 8 practice problems that are going to be going through identifying functions as linear, quadratic, or exponential. Then you want to, with the exponential functions, you want to tell if they are growth or decay. So this is just a review of everything that you've done up to this point. What does it mean to be linear? What does it mean to be quadratic? And now exponential is, does it have that exponential? So pause the video, try to identify with these 8, and then I will reveal the answers for you. So here are your answers. So you have a linear, exponential growth, quadratic, exponential decay, quadratic, exponential decay, and exponential growth. So with the exponential growth, remember your b is greater than 1, or it's a negative x and you have a fraction, right, like this one. And then our exponential decay, we had fractions as our b less than 1, and here we had a negative exponent, so that would actually mean we would have a fraction, so that's why it's exponential decay. Quadratic, we have x squared, linear, just the x. Great. Okay, now, so we can identify what a exponential growth and decay look like. Now we're actually going to go into graphing the exponential functions. So we're going to graph the parent function f of x is equal to 2 to the x. Then we're going to go ahead and graph these 4 and see how we can compare them. I went ahead and graphed them on Desmos, took a screenshot, and posted that here. So let's go ahead and compare our parent function, 2 to the x, which is the red, to all of these other functions. So the first one is 2 to the x minus 2 minus 4, and that is the blue line here. So identify the end behavior. Well, as it goes to infinity, we go to positive infinity, and as we go to negative infinity, this is going to go, I know you can't see here, but along the line y equals negative 4. So that is also our horizontal asymptote, y is equal to negative 4. We can identify the domain as all real numbers. The range is at negative 4 up to infinity. And then finally, last thing we want to do is identify the translation from this parent function. So from the red, we can see that the blue function, it definitely went down, and it looks like it went over as well. But by how much? That's the question. Well, it went right to, and down 4. Okay, so this point 0, 1, excuse me, went to negative 4. Nope, it didn't. It went to negative 3, 2. Now our next function, 2 to the x plus 2 plus 3, pause the video actually right here and try to complete it for our next one, this one, and the bottom 2 as well. So here's what happened. So in the second one, we moved it left 2. This function moved left 2 and up 3 compared to our parent function. Hopefully you paused the video and were able to give, these ones a try as well. So 2 to the negative x, what that did was it made a horizontal reflection, and the minus 1 brought it down 1. So it's a horizontal reflection because that negative is on the x, and the x-axis is a horizontal line. That's why it's a horizontal reflection. Here, though, our 2, that changed our y value, changed our outcome of the f of x. So that's why it's a vertical stretch, because it's related to the y. Alright, let's try to summarize now. Oh, that answer shouldn't be revealed yet. But here's our general form. Y equals ab to the x minus h plus k. H will move the graph left or right, whereas k will move the graph up or down. And the asymptote will be at y is equal to k. So that's our general form, and that's what's going to happen. What you will see on the rest of this page are some practice problems. I'm going to end the video here, though, and there will be another video going through these practice problems. Okay, so make sure that you do that, and watch the next video, which is going to be on the word problems as well.